Okay, so assalamu alaikum and welcome to the fourth video installment for your revision for grade 8 science. I'm Ms. Fatima Abbas, grade 8 science teacher here at Al Fadl School in Yaha. We are going to go ahead and look at the next outcome, which is to recognize how light interacts with matter and differentiate between transparent, translucent, and opaque. Okay, so light waves interact with matter in different ways. So before we continue, that word interact in Arabic is ta'afalun. So when we use the word interact, we're talking about how that wave is going to interact or with other objects. So let's first look at our first interaction. Here is going to be transmission. So here is transmission. And we know transmission is when a wave will pass through an object. So light waves can be transmitted through transparent objects. A transparent object is a material that allows almost all the light to pass through, and through which objects can be seen clearly. So air and glass are both transparent objects. We can see clearly through air and see clearly through clear glass, clear colorless glass, and it is allowing most of the light to come through. Now we also need to understand, even when there's transmission, there is a small amount of absorption and reflection here. But with these transparent objects, most of the light, the primary interaction that takes place is transmission, because most of the light is going through. Light can also be transmitted through translucent objects, such as wax paper, frosted glass, tinted windows, sunglasses. All of these allow for the transmission of light. So light is being passed through. What we do notice here is that we can't see clearly through it. So we can see the shape of the people, but we can't see exactly who's behind the glass. So again, transparent, I forgot to mention, is shifaf. I'm not going to write it out. You guys know shifaf. And then translucent is shibh shifaf. So remember the English words. These words are important. We have translucent and we have transparent. Then we have opaque objects. Opaque objects are materials through which no light can pass. So that means the light is mostly being absorbed. So it absorbs most of the light. You cannot see objects through them. So when we look at this picture here, the wood panes here are opaque and the curtains are also opaque. They are absorbing yamtas. They are absorbing most of that light. Here we have reflection. Opaque objects will also reflect light. Transparent and translucent objects are also reflecting light. That's why we are able to see them. The objects we see because they are reflecting light. So we can see how the light is coming from the light source down to the object. It bounces off the object and into her eye. So light is being reflected, and that's how she's able to see the words in the book. Same thing here. Light is coming from the light source to the apple, and then in this case, red light waves are being reflected into the eye. Okay? So here's a breakdown of what's happening with all three materials. We have transparent materials. such as air and glass, where all or most light passes through and forms a clear image. So we're having, in this case, it's always going to be most light, because a small amount of light will be absorbed, and some light gets reflected as well. And we know that because you guys are always standing in front of windows, clear windows, and you're able to fix your Shaylas or look at yourself even in those windows. So most of that light is being transmitted, but a small amount of light is going to be absorbed. Translucent materials such as wax paper, frosted glass, sunglasses, tinted windows. These translucent materials are letting some light pass through. The images that form are going to be blurry or slightly different in color because the translucent material. Remember, some light is also going to be reflected here. Some light is going to be absorbed and stay in the object, but we're going to have transmission, absorption, and reflection with this translucent object, and we saw that in the video. The last type of material or medium is opaque. Opaque is ghair shafaf, so no light is going through. Light does not pass through. It forms no image, and our main interactions, our only interactions here are going to be reflection and absorption. We have no transmission here. So remember, transparent is shafaf, translucent shibh shafaf, and opaque ghair shafaf. So try to remember, yes, it's useful to know the Arabic so you understand the concept, but it is the English key terms that you need to know. Transparent, translucent, and opaque. So question, which of the following statements is not correct regarding properties, light properties, and how they interact? So we're looking at the properties and how they interact. So here we see people tint. So tint means that it's translucent to increase light absorption. So if it is translucent, it is going to increase light absorption, so we know that this one is true. So I'm just going to write T there. The brightness of a light is determined by intensity. The easiest way to think of intensity is to think about how strong it is. So the more intense a light, the brighter it will shine. So this one will be true. Let's take a quick look at that word intensity in Arabic, because it shows up with both types of ways. So yeah, so it's talking about how strong it is. Light travels faster in air than water. Remember, light travels faster in less dense material. Air is less dense than water, so this is true. After a vacuum, light will travel next fastest in air. Now, when light strikes a transparent material, so we need to remember, what is transparent? Transparent is shafaf. Is there an olive here? Sorry. Shafaf. I'm not sure if that's spelled correctly. Transparent shafaf material, most of the light is reflected. No, that is false. We know that when we're dealing with transparent materials, most light is transmitted. So transmission is the main interaction that happens with our transparent materials. So this one we know is false. Okay, so let's go to the next outcome. Explain how humans see things around them. And we mentioned it before. We can see things around us as light is being reflected off of the surface. So when we look at a flower, we see that they come in many different shapes, sizes, and colors. What happens between a flower and our eyes that enables us to see it? So this is what the picture is showing. Light comes from the light source and is reflected off of the flower. So to see the flower, light reflects off the flower and enters your eye. That's how we can see it. If there is no light to reflect off the flower, we cannot see it. What happens when light reflects off a smooth, flat surface, such as this plane mirror? Remember, plane mirror is a flat mirror. It's opaque, but we are having a high amount of reflection off of there. So when light interacts with an opaque object, like a flat mirror, the light will bounce off, reflected regularly to form an image. So let's see. Not only should we know that it's forming an image, but we should know that this is a virtual image. So no light passes through the image. The image is behind the mirror. And when we talk about convex and concave images, concave and convex lenses and mirrors later, it will be useful to know what a virtual image is. So no light is passing into the mirror. It's being reflected off of the mirror, but the image appears like it's in the mirror here. And I'll go over that definition again later. So, here's our light source. And we can work on labeling this out a little bit. Here's our light source. This here would be our incident ray. Coming from the light source. So remember, the light source can be on any side in these pictures. Usually we had it on the left side, but in this case it's on the right side. So that's our incident ray. And then we have our incident angle. And here we have our reflected ray. And then we also have down here our reflected angle. Okay, so I'm just going to draw, here's our reflected angle is right there. And our incident angle is right there. So in order to see the object, the light has, the incident ray will be reflected into the eye, and then our brains can process that object. So light sourcing means light waves, light rays are reflected off an object and enter the eye. So let's look at this question, seeing a flower. We went over in class what happens between a flower and our eye that enables us to see it. The light in the room lights up the flower so our eyes can see it. Not quite. A lot of you were picking A in class, but that was not right. Something goes from our eyes to the flower so we can see it. No, our eyes do not emit anything. Something goes from our flowers to our eyes so we can see it. Maybe. Particles of color travel. No, particles of color do not travel. Something goes back and forth to our eyes. Nothing is going back and forth. So the best correct answer is choice C. All of these have elements that sounds correct, but we need to remember that something here would be light is reflected off the flower to enter our eyes. Okay? Next outcome here, question 12. State the law of reflection and assign the angles of incidence and reflection on a smooth surface or on rough surface. So we looked at this already by labeling our angle of incidence, our incident ray and reflected ray on the last page. So hopefully you guys remember this. Remember, the incident ray comes from the light source. So the light is moving from the light source to the mirror, forming a specific angle called the angle of incidence, or the incident angle. And remember that this angle of incidence is measured from the normal. I spoke about perpendicular in a previous video, but remember, perpendicular is a line, is when two lines cross at a 90-degree angle. So the normal is a line that is perpendicular to your mirror. So we can see that this is a 90-degree angle between the mirror and the normal. And we're measuring our angle of incidence from the ray to the normal. So the angle formed when incident ray meets the normal, an imaginary line perpendicular to a reflecting surface. So again, this is our definition of a normal. The angle of reflection is the angle of the reflected ray to the normal. And we need to remember the law of reflection says when a wave is reflected from a surface, the angle of reflection, so this is the important part here, is to remember the angle of reflection is always equal to the angle of incidence. So this is the important part here, as I was stressing in class. And we can see that here. Here's an example of reflection. If we drew the normal coming down the middle here and measured the angles, we would see that the angle of incidence is always equal to the angle of reflection. The angle of incidence, remember, comes from the light source. So here's our light source. Here's our angle of incidence. Our incident ray. Here is our reflected ray going this way. Okay? And here's another example of reflection. We can see that the light is reflecting, so that it's coming from the light source to the tree, to the mirror, to the water, and then being reflected into our eyes so we can see it if we're standing here. Okay, and that's how the image is forming in that water. So from the light source to the object, bouncing off the object into the lake, and then going into our eyes so that we can see it. A surface that reflects light to form an image is a mirror. Your brain knows that light travels in straight lines. Your brain perceived where the light rays appear to come from, not their actual path. So this is what, as I mentioned earlier, our virtual image. If this is our mirror, light is not actually traveling into the mirror. So these rays are virtual rays, not real rays. So the virtual rays will travel into the virtual rays form, and our brain is actually able to make the image or form the image. So light is not actually passing through the image. There's no light here, even though the image appears to be there. It is a virtual image, so it is a not real image. Okay? Hopefully this makes sense. I went over it several times in class. So a virtual image is an image that appears inside or behind the mirror, and no light is passing through it. Those are the two things that we should make sure we understand. Now let's look at type of reflection. We have regular reflection. This is the reflection we've been talking about. It happens on a smooth, flat surface. It's easy to understand. We can clearly see that the angle of incidence is equal to the angle of reflection. Here we have diffuse reflection. Diffuse reflection happens on a rough or uneven surface. So this is a rough surface. It's not smooth like this one here. So on this rough surface, we have diffuse reflection. The angle of incidence for each of these is still equal to the angle of reflection. The difference is, at any given spot, the normal is going to be different. So because this is not a smooth, flat surface, it's 90 degrees will look different at each spot. I hope that makes sense. So if I were to draw the normal here might be like that, because this surface is not parallel to the ground, let's say. Or here's my normal here would be like that, because again, the surface is not parallel going all the way across. And again, I hope this makes sense and I'm not using too many technical terms here, but diffuse reflection, the light is just going to be spread out, and light will be reflected in all different types of directions, or all different directions, because each bump in this surface has a different normal. Scattering, this happens with dabab, so when we have fog or when there's dust in the air. When waves traveling in one direction are made to travel in many directions, so all the light rays are coming in, let's say, from the sun, and they're bouncing or being reflected off of the dust particles. Some we can even see being reflected multiple times. So this one is coming in, being reflected, and then being reflected again. This is called scattering. Let's look at the word scattering in Arabic. Or let's just do scatter, or scattering. I'm not sure if those words have the same meaning. So scattering just means to spread out, kind of. So when we look at this picture, we can see that light will be scattered as it hits or it's reflected off of the many dust particles, or sometimes if it's dabab, like the fog in the morning, it will be scattered off of each particle of water droplets, or if it's smoke, then the smoke particles. Whatever it is, scattering makes it hard to see because the light is going in all different directions. So, which object has a surface that reflects light rays in the functional manner shown in the model above? So we know a convex mirror is going to be a mirror that faces this way. So it's not going to be our convex mirror, because this doesn't look like a convex mirror. We know a glass window will allow light to be transmitted all the way through, and this is not letting light be transmitted through. A polished silver spoon could be either convex or concave, depending on which side we use it. So this does not look like a spoon. Maybe you don't know what is meant by pond with ripples. So again, you don't have access to Terjema when you're taking your test, but we have access to it now. So some of these words we can look up. We can use the process of elimination. So this is what I was trying to help you do. But this is a pond with ripples. So by the process of elimination, we know it's not the other three that only leaves a pond with ripples. And ripples are just small waves that take place in water. So this is like a pond with ripples. What type of reflection is modeled? It's not a plane mirror, so we can see that it's not a plane mirror. We didn't talk about, or in this video we didn't talk about real images yet, but we know that this is not a real image or a virtual image. It's not regular reflection, because regular reflection happens in a plane mirror. This leaves only diffuse reflection. So remember, diffuse reflection diffuse reflection is reflection that's happening on a rough surface or an uneven surface. Okay, so let's look at the next outcome where we're looking at convex and concave mirrors. Fairly simple ideas. So conclude the type of image that will form from concave or convex mirrors depend on the object's position. Okay, so we spoke about virtual images before. So virtual images are images that are forming in the mirror. So a convex mirror, let's look at convex mirror first. A convex mirror is a mirror that is curved outward. So it's curved outward. These are the mirrors that we see sometimes in the garage. Or parking lots. So these that are taking in the corners often of parking lots or alleyways. I see them all the time while I'm driving around here in the UAE, so that we can see what's around the corner. Convex mirrors, the mirrors that are side view mirrors, are also convex mirrors. Why do we use convex mirrors on the cars? It's because they are spreading out light rays, so we can see more of an area as those light rays are being spread out in the mirror. But these are producing virtual images only. So convex mirrors are producing virtual images. just like plane mirrors. So convex and plane mirrors are producing virtual image. A concave mirror is a mirror that is curved inward, and the way I was trying to help you remember this is because the word cave here, we walk into a cave, so caves are inward. And what happens with the concave mirror is the concave mirror allows light to converge at the focal point. For this reason, concave mirrors can do both virtual and real images, depending on where the object is located. So light rays come together, they converge after they strike the surface of a concave mirror. Okay, and let me just go to YouTube really quickly. I know this video is kind of long already, but the video, let me do this. Where was that? No, I can't find that concave mirror experiment we were looking at before. Okay, I will just, if I find it, I'll share it as a separate video. But light rays come together, they converge after they strike the mirror. Some things that you should make sure you know from this is the optical axis. Optical axis is a lot like the normal. It goes through the middle. It's perpendicular to the middle of your mirror. So here is your optical axis. You should also know your focal point, particularly the focal point of your concave mirror, and then you should know your focal length. So focal length is the distance from the mirror to your focal point. Focal point is where all the light rays will converge, and your optical axis is a line that goes through the center of your mirror, and that's a perpendicular line. Okay? And here we go with those definitions. Optical axis, perpendicular to the center of the mirror. Focal point is where light rays parallel to the optical axis converge, and the focal length is the distance from your mirror to your focal point. Here it tells us that convex mirrors and plane mirrors form only virtual images, which we spoke about, and concave mirrors can form virtual images and real images. The image a concave mirror forms depends on the object's location to the focal point. And again, the video that I will share with you will give you a good view of this. A virtual image forms if the object is between the focal point and the mirror. So if I put my object between the focal point and the mirror, right here, it will form a virtual image. A real image will form if the object is, so I'm going to change colors, beyond the focal point. So if the object is beyond the focal point out here, then we will get a real image to form, and that real image would be upside down. Maybe I should make the second arrow different shade of blue, so this is our image that will form. And if I make, this is our virtual image that would form in there. Okay, I hope that makes sense, but again, I'll share another video that does a really good job of explaining or demonstrating with the candle. We watched that in class before. So here's our convex mirror. This is our virtual image that we are going to have here. Here is our concave mirror, and this is our real image. So this is our real image. So remember, we can use concave mirrors to make projectors, right? Because a real image, light is passing through our real image. If it's within one focal point, so between the mirror and the focal point, then we're going to have a virtual upright image, and it's magnified. How does the structure of convex mirrors support the function of side mirrors on a car? Is it A, convex mirrors only reflect images to the driver, makes with the normal on the mirror? That is not true. Convex mirrors will spread out the angles out, so the driver can see much larger amount of space. We know that convex mirrors spread the angles. Convex mirrors will spread the angle out so it can see smaller amount of space. No. Why would a driver should want a larger amount of space? So because it's being spread, then we know it's a larger amount of space. So this is true. Moving on to outcome 14. Explain how does a lens affect the size of an image and relate it to real-life examples. Define the index of refraction and its value in different mediums. Light travels very fast in a vacuum, so unlike a mechanical wave such as sound, light can travel in a vacuum. It travels up to 300,000 kilometers per second. Light travels more slowly when it moves through a medium, such as air, glass, or water, because the atoms of the material are going to interact with that light and slow them down. As a wave moves from one medium into another, its speed changes. The wave will change direction. This is called refraction. So as the light is traveling, so here's our incident ray, as it is traveling from air, which is a fast medium, to glass, which is a slow medium, we can see that it is getting refracted and it is going to slow down. When it's going from a fast medium to a slow medium, it will bend towards the normal. So we can see that it is refracting towards the normal. This angle right here gets smaller. So if I were to make a little dotted line to demonstrate, or another line to demonstrate how it would keep traveling. If it was straight, we can see that the angle of refraction gets smaller as it goes into the slow material. The index of refraction indicates how much a medium can change the direction of light. Medium with high index of refraction is called slow, because light moves more slowly through it. So we can see glass here has a high index of refraction. A medium with a low index of refraction moves fast, or light moves fast through it. You always see the fish further away than the fish actually is. This is a virtual image because light is getting refracted as it passes through the glass. So again, as light is going from a fast medium to a slow medium, it bends towards the normal. So this is our angle right here. And then when it moves from a slow medium to a fast medium, it bends away from the normal. So we can see if this angle is 30 degrees, maybe this angle here is 45 degrees. So we can see, these are just arbitrary numbers that I'm picking. We can see that the angle of refraction changes as it is moving from fast to slow and then slow to fast. So here it bends away from the normal, here it is bending towards the normal. Which of the following arguments identifies the best explanation about a concave lens being used to start a fire? So let's think about a concave lens. We did not talk about concave lenses yet here, but this is our concave lens, would look like this. We should know that a concave lens will diverge light as it passes through. So, a concave lens will focus the sun's light. No, concave lenses do not focus light. Because the sunlight comes from all directions, a concave lens will straighten the light. No, they do not straighten the light. They cause light to diverge, as this picture shows. Because a concave lens diverges the light, the sun's light will not focus on a paper. This is true. It diverges light. It will not focus the light. And concave lens will focus the sun's light? No, because it doesn't focus the light. It is a convex lens that will focus the light. Okay, through a lens. A camera lens can make an image larger or smaller. How does a lens affect the size of an image? I will just come straight down and circle here. The size of the image depends on the shape of the lens. And we will look at lenses more when we talk about the writing question. But the size of the image depends on the shape of the lens. So the size of whether the lens is convex or concave will make a difference, as well as the thickness of that lens. So illustrate the functions of the human eye and its main parts. We have two convex lenses in the human eye. One is the cornea. So as light passes through the eye, we can see it happening here, and it passes through the cornea. It starts to bend a little bit, so it starts to refract or converge towards the lens. This part of the eye, which is simply called the lens, will cause all of that light to converge onto the retina back here. So I would say the retina is another part of the eye that we should make sure we are familiar with. So we have the cornea, which is a transparent tissue, serves as a lens to start to converge the light. Then we have a lens, which is another transparent object in our eye that converges the light, and it converges the light onto the retina. The retina can then send the signal to the brain. Some vision problems are caused by the cornea. So when the cornea fails to form an image on the back of the eye, when we say back of the eye, we're specifically talking about the retina. Then we can use corrective lenses or glasses can be used to make sure that light gets directed properly. Some lenses will diverge the light, so that means that they would be concave, and other lenses will converge the light, which means that those will be convex lenses. So again, and let me make a note here, because you can see I'm even getting tripped up. Concave lenses will diverge. Convex lenses will converge the light. And remember, that's opposite when we talk about concave and convex mirrors. So question, which part of the eye can change its structure as a function to form a focused image? That is going to be 3. So we would simply have to look back at this picture, and it tells us transparent structure that can change shape. So it has these little muscles attached here, ciliary muscles, that will allow the lens to change shape. So it is the lens that will change shape. This is a simple definition question. That is this part right here, changing shape. Okay, so I will stop this video here. I know it's a little bit long. Thank you for watching, and I'll catch up with you on the next video, which looked at the writing question.